binomial distribution last time. And now we're going to the only continuous distribution. We first start by studying a special case of it. So we're going to be looking at the normal distribution in the next 2 days. We start with the special case of the standard normal and then move on to the more general case. First, though, a little bit more background on continuous random variables. Continuous random variables are typically represented by a density curve. Which we typically look at it as a probability density function, a PDF, and that is represented graphically as a curve. The probability of the random variable falling between two values is the area under the curve between those two values. And that is an integral, which is calculus. So again, for the most part, a lot of this you're going to take my word for it. The area under this curve will always be 1. That is equivalent to the sum of all the probabilities being 1. If you study calculus, you learn that integration is actually a sum. I kind of mentioned this already. Area under the curve between two values has two interpretations. Proportion of the population whose values are between A and B. Probability that a randomly selected individual will have a value between A and B. And probabilities are also proportions. The one random variable we're looking at is the normal distribution. We say it's normally distributed if the relative frequency histogram of the random variable has the shape of the normal curve, the bell shape. So that is several normal curves, right, for different means and standard deviations. You're lucky that you don't have to work with this right now. This is the density function. That is not fun to work with. So probability of normal distribution It is always symmetric about its mean. The mean, median, and mode are all the same. Area under the curve is 1, that's for any random variable. Symmetry means that exactly half the area is to the left of the mean and half the area is to the right of the mean. Asymptotic to the x-axis, so the x-axis is a horizontal asymptote. And the empirical rule applies. This is where the empirical rule becomes really necessary. The rest of the semester, for the most part, is dealing with normal curves. Distribution can have any mean and any positive standard deviation. The mean and the standard deviation are the parameters associated with a normal distribution. Right? So we would typically write that to represent that a random variable is normally distributed with a mean of mu naught and a standard deviation of sigma naught. The most basic normal distribution is called the standard normal. It is the normal distribution in which the mean is 0 and the standard deviation is 1. Remember z-scores? This is where the z-scores come from. Generally speaking, when dealing with the standard normal, the random variable used is a capital letter Z. Remember, that is always going to be a normal distribution of mean 0 and standard deviation of 1. Finding areas between z-scores requires a bit of calculus. So we're not actually ever going to calculate them. Not by hand. We will do one of two things. Either read it from a table, table B, located on Blackboard, and I will be referencing it today, or technology, either calculator or Excel. We will do all three today. Normal is the same as the binomial. There is a function on statistical calculators for the normal distribution. Pleasure. Z sub alpha will represent the z-score that has an area of alpha to the left of it. And I have to be careful because there are a lot of Z tables out there and they don't all read the same. The table that we'll be using is read as area to the left of the z-score. Teaching an online stat course where the z chart they give is read as the area, positive area between 0 and z-score. But the tables will generally have a diagram that shows you what area it's given. So this is what our table will look like. So it's finding area to the left of your z-score. I'll let you read through those on your own. So I'm actually going to develop these techniques as we work through the examples. Let's go ahead. Remember capital Z, standard normal. So we want, what's the probability that Z is less than 0.37? Well, that is the area under the standard normal curve that is to the left of 0.37. Right, so using that notation, we want Z sub 0.37. So this is the table. So what we're going to want to do is look first in the first column. That will give you the first two digits, the units digit and the tenths digit. We want 0.3. First page is all the negatives. Second page is all the positives. Right, there's 0.3 there, right? Now look for the column of 0.07. That would give you 0.37, right? There's your possibility. .6443. Now we want probability that Z is larger than negative 1.25. Here's what we're going to do. Something like that's good enough. That's the mean of 0, right? We want negative 1.25, right? That's what I was looking for, greater than negative 1.25. So maybe right about there is what we're looking at. So the area that we're looking for is that area, right? But the table only gives that area. So how are we going to get our desired area? Well, what do we know about the total area? What does that total area have to be? What is that total area? Does that mean that the sum of those two has to be 1? So our area of interest isn't going to be 1 minus the area to the left of the t-square. But mind you, that area would be that probability, which is the complement of the probability that we want. So we're still using rules of complements. So I have to look at the table. Negative 1.25, that is the first page. Look for negative 1.2. Which unfortunately you are not able to see my cursor, which is actually right here, right? Now go to the 0.5. I'm just going to count. 0, 1, 2, 3, 4, 5. 0.1056. It's not just 1 minus that. It's going to be what? 8, 9, 4, 4. Now the probability between two z-scores. Good enough. What are the two z-scores we're looking at? Negative 0.85. And 1.42. That is the area that we're looking for. But our table only gives us areas to the left of scores. So what two areas do we know? We know that whole area. Right? But we also know that area. Right? So what is our area?
So, 1.12 minus the area negative 0.8.
And both those areas are on the table. That is what was listed here. Right, part A was number 1 there, right? which is fairly simple. B was number 2, and C is number 3. In terms of probabilities, this here, why does my cursor not show up anymore? Oh, it does, it's just very small. Ah, that works, okay, so let me use this for my point. Except now you don't want to show, are you serious? You don't want to show? That shows, that'll work. So that, what is going on? There. I don't know what's going on, right? That is the probability that Z is less than 1.42, right? And then that is the probability that Z is less than negative 0.85. So I'm going to rewrite this in terms of probabilities. .42 first. Come down to the positives. 1.42. That 0.9222, right? Just quickly get that on here. And then negative 0.85. .1977. So we just want that difference. .7245. And there's our probability. Right? So just requires a little bit of arithmetic and being able to read the table to do it by hand. For now. Take a more advanced stat course that might require you to use the actual calculus itself. So you'll find it under the section out on Blackboard. I would recommend you go and download it. But it also would be available like when you go to take the Unit 3 test. You'll see the resources folder is also going to be in there when it becomes available. It might also be under the textbook folder at the very beginning. It's lots of places. There's also a binomial table. I don't know if I mentioned it, table A. There's a table of binomial values, but I didn't use them because it's quite simple to do using technology. But I think that table will also be under the resource folder for the Unit 3 test. Now we get to work in reverse. They're not going to give us a z-score. They want us to find the z-score. Find the value so that the probability that z is less than or equal to z is 0.9750. Right. In other words, what they're looking for find that alpha. Find the z-score that has an area to the left of 0.9750. You can save yourself some time. 0.9750 is larger than 1/2, which means the z-score has to be positive. It's exactly half of the areas to the left of 0. So we're going to come down here. Now, instead of looking at the column for the z-score, we're looking in the actual table itself and looking for 0.9750. So 1.9, I see 0.9713, so that's a good start to look, right? Let's just look over, there it is. Now the question is, what is that? So it's 1.9, 0, 1, 2, 3, 4, 5, 6. So that is our z-score, 1.97. Find z, so the middle 80% is between negative z and positive z. We want us to find the z that makes that true. Right? Let's say that this is z. Try and make it somewhat look like it's the same distance. Negative z, right? So it's only telling us it's going to be symmetric about 0, which is going to be useful. Well, if 80% is there, how much is left? But it's symmetric, so how much is in each tail? Because it is symmetric, you can either find that one or that one. It doesn't matter. The easiest one to find in the table would be that one right there, right? That's the one I'm going to look for. So we've already determined it's going to be a negative z-score, so we'll come up here, and we're looking for 0.1. Why is it not showing on there? And I can clearly see it. It's going to be somewhere between here, right? What is that? That is negative 1.2. That'll be what, 9 and 8? So negative 1.28 and negative 1.29, somewhere there. Generally speaking, if it's going to be between two z-scores, we just take the average of those two z-scores, which would be negative 1.285. However, if you take a look at this, of the two, negative 1.28 and negative 1.29, which one is closer to an area of 0.1? The 1.28 is significantly closer, right? So I'm going to use negative 1.28 as my z-score. It's probably more like negative 1.2805 or something. But we're only going to go to 2. But that's not what I want. I don't want the negative, right? We want z so that it's between negative z and positive z. Z is 1.28. So we're looking for an area of 0.1, right? And we go, well, it's not on the table. It's going to be between here, right? But it's a really close to the 0.03, so I'm taking that as my value. Yeah, because that's what it's asking for. Because it's symmetric and we're dealing with the z-score, it will be negative 1.28, and if you look, area to the right that has 0.9 will be positive 1.28. That one shouldn't be on there. So we're just going to pretend that's not there. That's for next time. All right. Those two were the by hands. We're doing it by hand reading the table. This one is calculator, I believe. Let's go ahead and load that up. So you need to determine where your statistical distributions are. If you remember, for the Inspire CX2, it's menu, statistics, distributions. The very first two, right? PDF, normal CDF. Do you remember what the difference between the PDF and the CDF were? Cumulative. I don't think we're ever going to use the normal PDF. You can, but it's just a nasty formula. And we don't typically do it in an elementary stat course. So we will only ever be working with the CDF. Lower bound? Okay, so sadly, the calculators that you're allowed to use will not let you do negative infinity as the lower bound, or positive infinity is the upper bound. Mine can. So we'll have to kind of make do. I think that's as high as we go. 9E999. Now let's real quick take a look at the probability it wanted us to find again. Greater than or equal to 1.75. Well, that means 1.75 or larger, right? .75 would be the lower bound. And then the upper bound would be technically infinity, but I can't do that, so 9. Again, if you look on your calculator, that double E key, E, do you know what that means, what E means? So if I write that, do you know what that means? That's scientific notation. That's 9 times 10 to the 999. So it's a very, very, very large number. I don't know what your calculator will be, but mine is default standard normal, which is nice. I don't have to change the mean or the standard deviation for this. Now if I just hit OK, there's the area. We're only going to go up to 4 decimal places. 0.0401. What I'll do is this. Find z where the probability of z less than or equal to that value is 0.88. Here, I'm going back to distribution, but this time I want the inverse normal. Right? Normal, CDF gives you area. Inverse normal, you put in an area and it gives you the value. If I'm not mistaken, it's going to give value that is less than or equal to. It'll never give you greater than. So for that, you will have to adjust. Area was 0.88, right? And it's the standard, so mean and standard deviation, 0 and 1 respectively. To 2 decimal places, 1.17. I'll just screenshot that. That was also shouldn't be there. Probability that z is less than or equal to 1.25. This time on Excel. And so this example is going to be strictly Excel. Zoom into 200%, so that is going to make a difference. Binomial bit I know, so it's really small on here. That's still small. That. Norm, if it's standard, which ours is, dot s, dot this. So this is the standard normal distribution. Put in the z-score that it's going to be less than. It was 1.25. And then true to say that it is going to be cumulative. There's your probability. That they wanted the z-score for the 95th percentile. What does 95th percentile mean? You think way back when we looked at percentiles.
Does doesn't it mean that 95 people did worse than you did?
Not necessarily 95 people,
Percent of.
right? So 95% of the values are smaller than it. Well, in this context, that means that the area to the left would be 0.95, right? So we come in here, equals, I think it's norm dot INV for the inverse norm. Dot S dot INV, standard normal. You need to put in just probability to the left, area to the left, 0.95, and that will give you the z-score, 1.645. Let's get that Excel file saved. I'm thinking of it. That's a standard normal. Questions in standard normal. Thursday, we're going to look at the normal distribution. If you're not using technology, and you have to do it by hand, what we have to do is we have to standardize the distribution. The standard normal, right? That means make the mean 0, the standard deviation 1. So that means we're converting our values to z-scores. And then we'll be using the same technique as we did today. Of course, with technology, it's a lot easier because you can just put in what the mean standard deviation is and have it give you the area. So again, we'll be doing 3 things, right? We'll do it by hand using the Z table. Then I'll use the calculator, and then I'll show you on Excel. Okay, and then after that is central limit theorem. And then that's the end of the 3rd unit. So the end of the 3rd unit is coming up. I think all of next week is central limit theorem, because I think it's broken into 2 parts. Central limit theorem for mean and central limit theorem for proportions. Then after that, we get to do my favorite thing. Hypothesis testing. And so just keep in mind that your second project is due the 20th. Coming up on, let's see what this is. Only a few weeks away from that. This is already week 10, so we're almost 2/3 of the way through the semester.
We're still able to submit the AI assignment today, right? We're still able to submit the AI assignment today, right?
When was it due?